We begin this lecture with exact solutions. This is the topic of this lecture number 16, which is the opening lecture for the second unit, you can say, or second module of the course. In this lecture, my learning objectives are to understand the meaning of exact solutions of Navier-Stokes equations. So, what do we mean by exact solutions? And these exact solutions are dominated by these unidirectional flows. So, there are some very specific types of flow configurations which can provide this kind of a flow. We will look into it in detail, what is a unidirectional flow and these flow configurations in which this can be realized. And lastly, we will rather demonstrate a very systematic approach of simplifying the Navier-Stokes equations for the viscous laminar flows of Newtonian fluids. Of course, I have been mentioning it earlier also for incompressible homogeneous constant property model, and the simplification will be for the unidirectional flows. So this is my learning of. These are the list of my learning objectives. Right. So we begin with the exact solutions. So, what do we mean by an exact solution of Navier-Stokes equations? Let us try to understand that first. So, a solution of Navier-Stokes equation, which is a particular solution for a specific viscous flow problem. This is what we mean by solution of Navier-Stokes equation. So, since there are two keywords, exact solutions, so I am first trying to bring your attention to the fact that when we say solution of Navier-Stokes equation, we mean a particular solution for a specific viscous flow problem. Okay, so one should have a specific viscous flow problem to talk about a particular solution of Navier-Stokes equations. Because of the nonlinear character of Navier-Stokes and coupled nature, there are no, you can say there are no general solutions. Okay, we can only talk in terms of particular solutions. Right. Now, what does the word exact qualify or mean? By exact, we mean mostly analytical solutions. Analytical solutions in the form of velocity, function, pressure, or motion pressure distributions or function. So, just as you know what is an analytical representation of some kind of a relation, basically through functions. So, exact solutions are also you can say functional form solutions of velocity and motion pressure. So, velocity and motion pressure will be represented by some analytical relations or functions. Okay. So, this is what is the meaning of exact solutions. Now, we have already seen that Navier-Stokes equations are nonlinear coupled PDEs and partial differential equations. So, exact solutions are very rare for these kind of complex system of partial differential equations. In fact, they are only possible for very simple flow problems. So, what do we mean by simple flow problem? There is simplicity of geometry and boundary conditions, and there are some, in addition to the simple geometry and boundary conditions, we have some simplifying approximations or assumptions about the flow. Better word is approximations. Okay. So, through these simple problems together with their simplifying approximations, they appear to serve the academic interest, though these simple problems together with their simplifying approximations, they appear to serve the academic interest in terms of examining the solutions to viscous flow problems. But in addition to this, these problems will have, or they do have, some engineering or technical importance also. So it's not like they are only academic in nature, these simple problems for which exact solutions will be found and they will be discussed as we go along. But these simple problems also have some engineering or technical importance also. They are not totally sort of concocted or sort of overly simplified kind of academic problems. Okay. So when we will go through these problems, you will realize that they do have some engineering importance also. Now the types of exact solutions, let's move forward from here. So I would like to categorize so that we can categorization helps in understanding the similarities and differences in different types of exact solutions, and also it also helps in remembering the various types of exact solutions that we will learn in this course. So that's why I try to categorize. So can be placed in several categories. So broadly speaking, exact solutions have been put into two categories. One is the broad category of unidirectional flows, and the other is similarity solutions. Okay. Now, as I have indicated below the box, what is a unidirectional flow? So unidirectional flow is a flow where the velocity field or the velocity vector is simply aligned along one of the coordinate directions. Okay. Now, depending on the type of problem and geometry and the coordinate system that one may choose, that is all left as a specific kind of a exercise for a given problem. But in general, any flow to qualify as a unidirectional flow must have this property, that the velocity velocity field of any and every fluid particle in the flow for all times must be expressed as a component along one of the coordinate directions only. So it is not going to have all three components, but only one component. This is a unidirectional flow. Now, what is this? What is the other category on the other side? Similarity solutions. So these are some flows for which it is, though they are not unidirectional, but it is possible to reduce Navier-Stokes equations into a single ordinary differential equation. So partial differential equations getting reduced into a ordinary differential equation. So in mathematics, such ideas are grouped under the broad category of similarity solutions. Okay. So now going further down the tree of classification, the unidirectional flows I have further put into two broad categories, steady and unsteady, and I have already discussed these things in my lecture number 14 and 15, where I was talking of converting the equations into dimensionless forms. There also I had discussed these steady and unsteady aspects. So and the unsteady aspects further are put into transient character or transient analysis and unsteady forcing. So we have already discussed these things in my last few lectures, that in general one may have to deal with an unsteady flow situation if one is even if one is trying to investigate the transient character of a steady flow, or the flow itself is driven by some kind of a unsteady force, so it will always be unsteady under that force. Right. So moving on to unidirectional flows, because these are the most celebrated type of exact solutions that we have in fluid mechanics. In fact, they represent the majority of the exact solutions that are available. So these are very specific type of flows that can be realized practically under specific conditions. So when I said that these have some technical or practical importance also in engineering, it is because of this fact that you can realize them practically. That means you can recreate these unidirectional flows, or you can achieve them in laboratories. So there are some specific flow configurations, and I have placed them again into 4 categories. So there can be large number of configurations, but you can group them into 4 categories. This grouping enables us to analyze each one of them through a common procedure, you can say. So this helps in the analysis, because for example, in any let's say category 2, we are dealing with fully developed flows in pipes and ducts. So pipes and ducts can have different types of cross sections, but all of them can be analyzed through a common procedure, okay, and at least up to a certain extent. So that is why I am trying to group them into categories, so that I can discuss the common aspect of their flow behavior and the analysis through the governing equations applicable to those categories. So the first is fully developed flows in channels, and second is fully developed flows in pipes and ducts, and third is annular flows in cylindrical geometries. So fourth is and the last is radial flows. So by and large, the categorization is quite self-explanatory in the sense that, for example, if you look at the first category, and the figure is shown at the bottom, flow configuration 1. So when we say fully developed flows in channels, first pay attention to the word channel. What is a channel? Flow channel. Channel means I have 2 large planar surfaces. As shown in the figure, I have a rectangular kind of large two large plane surfaces, and they are separated by a gap which is say h, and it qualifies as a channel if the gap is relatively small in comparison to the width and the length of the planar surfaces, which forms the channel. Okay. Now, as I have shown, you can generate a unidirectional flow in this gap if suppose you have a uniform flow shown by the red vectors here, shown to be entering this channel, and the vectors are all directed along the coordinate x direction, okay, and y and z coordinates are also shown. So since I make the flow uniform flow enter along the x direction, then what really happens as the flow enters the channel, the no slip condition immediately springs into action from the top and bottom walls, and so viscous effects start to grow in the channel, and after some distance from the inlet, you will find that the viscous region or the layers from the top and bottom actually grow to meet, and once they meet, it becomes a fully developed viscous flow. So in the entrance region where the viscous layers are still growing from the top and bottom walls, we will not find unidirectional flow. In fact, there will be velocity components both along x as well as in a direction normal to the planar surfaces, which is y. So if you, for the time being, you leave this inlet flow or developing flow region, then once the viscous layers from the top and bottom surfaces, they meet, and the flow becomes fully viscous in the entire gap, then we can practically realize a unidirectional flow where all the fluid particles are seen to move along the length of the channel or along the x direction. So my unidirectional flow for this category will be simply represented as vector v is equal to u, which is the x direction velocity component. And since I don't have any other information, so I am writing in general that this u can be a function of all these space coordinates x, y, z, and it may be unsteady also, so function of time, and so this expression is valid for this flow configuration 1, unidirectional flow. Now moving on to flow configuration 2, which has been named as fully developed flows in pipes and ducts. So here I show a figure where a pipe of some general cross section is shown on the right, that is on the right top image. Please focus there. I am currently talking about that image, flow configuration 2. So in that image on the left I have shown a pipe whose cross section is some general kind of a shape, and of course the cross section is the same along the length of the pipe. It is not allowed to vary, so it's a uniform cross section pipe or a duct. Okay, because if it is not uniform, then we will not get a unidirectional flow. So unidirectional flow is only achievable if the cross sectional geometry of the pipe does not change along the length of the pipe or duct. So again, the Cartesian coordinates are shown. So x being the direction which is known as along the length of the pipe or duct. So it is the axial direction, or the direction which is parallel to the axis of the pipe or duct. And again, the red arrows indicate that I am having a uniform flow which is entering this pipe or duct, and the uniform flow is directed along the x direction. So again, the same viscous layer growth from all the sides takes place as the flow enters the pipe or a duct, and at a certain distance downstream, the viscous layers which are generated by the no slip condition, they tend to meet, and once they meet, you have a unidirectional flow. This is very much realizable in lab also. Now, as I have said that the cross section is for the purpose of general analysis or treatment, it is kept arbitrary, but in practice, of course, the cross sections are having some regular geometries, like most common is a circular pipe, then you have rectangular ducts, and you can also have elliptic pipes or ducts, and even triangular shaped pipes or ducts. Okay, so these are some geometries which have their own importance and application in engineering practice. So that's why I'm considering these shapes. So now moving on to flow configuration 3, where I have mentioned this as annular flows in cylindrical geometries. So as you can see in the picture, there are two types of annular flows that are possible in cylindrical geometries. The first one on the left is having a larger radius pipe, and inside there is another solid rod or even another pipe of smaller radius. So the space between the larger outer cylinder and the inner smaller diameter or radius shaft or another pipe, that is the annulus that I am interested in. That annular region is the one where we are considering the flow. So as you can see, the flow enters again with in a direction along the length of the concentric cylinders or pipes, you can say, and so that is shown as with the help of cylindrical coordinates now, because they are more suitable for this kind of a geometry. So radial coordinate and theta coordinate, of course, you cannot see in this RZ plane, but I have shown it on the diagram just to make you understand that if you were to view this system from the end, then you will be able to see the r theta plane and therefore the theta coordinate. So now you can see that in the annular region there are two red arrows shown. So वो जो gap है between the inner and the outer walls, between the outer wall of the inner shaft or cylinder and the inner wall of the bigger or the outer pipe or cylinder, so the gap between is known as the annular region, and in that annular region the fluid is shown with a unidirectional motion. So it is directed along the z direction. So the velocity vector is written as Vz, having only Vz component. So Vz Ez cap, and Vz is of course I am allowing it to be a function of all space coordinates and time. Now there is another possible annular flow configuration which is between again two sort of concentric cylinders. The inner one is shown to be rotating in a counterclockwise direction with the angular velocity omega 1, and the outer larger radius concentric cylinder, you can say, or a pipe, is seen to be rotating again counterclockwise with the angular velocity omega 2. So when you have this kind of a physical scenario, and in between the gap between the inner rotating cylinder and the outer rotating cylinder, the gap contains a fluid. Okay, so in that fluid we expect some velocities in the sense and direction shown with the help of curved red arrows. Okay, so the fluid particles would have this kind of a velocity field. So it means that all the velocities of every particle, I can write them as velocity vector is equal to, and with the help of only theta component. Okay, so v theta. Okay, there is no radial velocity, and neither there is a velocity perpendicular to the plane of the figure, which is the z direction. So remember, ये जो systems हैं ये cylindrical coordinates में analyze हो रहे हैं. So there is a cylindrical coordinate origin attached to the center of the concentric cylinders, and you have the radial theta and the z directions, z being perpendicular to the plane of the figure. So this is how we can say that this is my flow configuration 3, which basically represents some annular flows. And this last one, where we have the rotating cylinders and the fluid in the annular region also undergoing a motion which is represented by concentric circular streamlines, you can say, because if the velocity field is as shown, then we will have concentric circular streamlines. So this flow is also known as a torsional flow. Okay, there can be other types of torsional flows also. This is while this is the case of an annulus, but you can have a single cylinder which is immersed inside a liquid or placed inside a liquid, and the cylinder is imparted rotation. So the fluid outside will also develop a purely torsional unidirectional flow. Similar is the case with the liquid filled inside a cylindrical container and the cylinder being imparted rotation. So the fluid which is inside will again develop a torsional unidirectional flow. Now coming to the last category, which is the radial flows. Now these are flows in these type of flow configurations or systems which I have shown. So the first one on the left is, as you can see, there are two circular discs which are separated with one over the other by a certain distance, and fluid enters the top disc with through the central aperture or hole. I have shown it with two red vectors coming vertically downwards, and as it passes through the hole, it enters the gap region between the two circular discs, and gradually the streamlines tend to spread all around in the radial direction. So apart from a very small region near the entrance, the fluid paths appear to be very radial, okay, in nature. तो वो जो छोटा सा रीजन है नियर द एंट्रेंस, अगर हम उसको इग्नोर कर दें क्लोज टू द इनलेट, देन वी कैन अप्रॉक्सीमेट द फ्लो एज प्योरली रेडियल यूनिडायरेक्शनल फ्लो. So V vector V is now represented with a radial component VR ER cap, and again I allow it to be a function of all space coordinates r theta z and time. Then on the right I again have a special type of a radial flow. So this is a converging diverging channel, or something which is different from the uniform channel that was in category flow configuration 1. So the channel is formed by two large planar surfaces which are inclined with respect to each other symmetrically about the center line. So they will have a equal inclination about the center line on either side, and now the origin for describing this kind of a flow, the flow enters from either end of this sort of flow passage formed by inclined planar surfaces. So if it enters from the left as shown with the help of two red arrows, as it enters from the left, then the fluid paths can be taken to be approximately radial, with the origin of the cylindrical coordinate system indicated at O, which is sort of a virtual or sort of a point which has been obtained by extending the planar surface sort of geometry on either side. If you extend the planar surface geometry, the lines will meet at a point O along the central median axis, and that O can be taken to be the convenient origin of the cylindrical coordinates. So any point P in the flow domain is having an angle theta and a radial coordinate r, and the fluid velocity approximately for all such points is along the radial direction indicated by red arrows. Right. So once we have gone through these four basic categories of you can say four basic flow configurations that are going to be having a unidirectional flow, then we can go about the general or sort of a very basic analysis of all these flow configurations without going into any specific kind of a solution or specific kind of a analysis with the help of some particular boundary conditions. We will only do a general analysis of these 4 configurations. The advantage is that if I do a general analysis of these 4 configurations, then some general features of these systems will come out of that analysis, and those general features and their simplified equations would then be available for any kind of a further you can say solution based studies for specific type of unidirectional flow configurations. तो जब हम कोई स्पेसिफिक यूनिडायरेक्शनल फ्लो कॉन्फ़िगरेशन डिटेल में एनालाइज करना चाहेंगे तो हमें ये जो बेसिक प्रॉपर्टीज़ यहाँ से जनरल सॉर्ट ऑफ एनालिसिस से मिलेंगी इन 4 कैटेगरीज के फ्लो कॉन्फ़िगरेशंस के लिए, तो वो बेसिक इक्वेशंस और सारी कैरेक्टरिस्टिक्स हमें वहाँ पे दोबारा से नहीं करनी होंगी और वो हम उसको एज अ स्टार्टिंग पॉइंट लेकर के आगे एनालाइज कर सकते हैं. That is what the advantage of this approach is. Now this approach is mostly not followed in many of the viscous fluid flow textbooks that are generally available. तो ये थोड़ा सा डिफरेंट है बहुत सी बुक से कि यहाँ पे मैंने कोशिश ये की है कि उनके जो डिफरेंट टाइप्स ऑफ जो एग्जैक्ट सॉल्यूशंस दिखाए जाते हैं किताबों में उनको थोड़ा सा कैटेगराइज कर लिया जाए, उनकी एक जनरल कैटेगरीज बना ली जाए और उन जनरल कैटेगरीज से उनकी कुछ जनरल कैरेक्टरिस्टिक्स लेट अस ट्राई टू स्टडी एंड आइडेंटिफाई. और द इक्वेशंस आर कैन आल्सो बी simplified for each of these categories. So the moment I get any particular problem, I will just quickly place it in one of these 4 categories, and by placing it all those general properties will apply, including the simplified sort of equations for these 4 categories, and I can then start off the further analysis on that. So this is the main advantage in looking at these unidirectional flows in the manner in which we try to look at them. Okay. Right. So let us now move on to this small exercise, you can say, of simplifying equations for the various unidirectional flows or flow configurations, you can say. So for all the categories of unidirectional flows, the governing equations for incompressible homogeneous constant property flow of a Newtonian fluid can be simplified. Now यहाँ पे मैं ये कहना चाहूँगा कि Newtonian fluid, while it is definitely going to give me a simpler kind of a scenario, but later on I can, in fact I plan to show you that even if you have a non-Newtonian fluid and you are dealing with a unidirectional flow, incompressible homogeneous constant property flow, which is unidirectional, but the fluid is non-Newtonian, then even then we can go for this kind of simplifications. So but that I will show later, and also if time permits then I will show it, but right now I want to state that Newtonian fluid gives the simplest possible scenario, so that's why we start with the Newtonian fluid. Once we have the simplified set of equations, solutions can be obtained for specific geometries and DC. तो वो जो पर्पस है ये जनरल काइंड ऑफ सिंप्लीफिकेशन का वो यहाँ पे मेंशन कर दिया गया. So type 1 configuration and type 2 configuration, let us take them together because both are analyzed with the help of Cartesian coordinate systems. So I can do it in a general way for both the configurations. These configurations involve fully developed flows in channels and ducts, as you know. Now when a uniform flow enters the channel or duct of uniform cross section, of course the channel or duct has to be of a uniform cross section, the no slip condition from the walls forces the formation of viscous layers that grow along the flow direction. So I've already mentioned this. So at some distance from inlet, the layers from all sides meet and a unidirectional viscous flow is observed, provided of course the flow is laminar. So this is something very important. Though I will not be mentioning it again and again, but unidirectional flow basically implies that the flow cannot be turbulent, because you will learn in the last unit that all turbulent flows tend to be multidirectional. They are not never unidirectional. The velocity has all the three components in space. So the basic idea of a unidirectional flow is not compatible with turbulent flows. It's only compatible with laminar flows. So keep this in mind, and I will not be mentioning it again and again. So let us now on the right, let us shift our attention there. So what is written? So unidirectional flow, the general feature is written. It has a velocity vector given as u, function of x, y, z and t, I cap. Now if I apply because this velocity field must satisfy the continuity equation as well as the momentum equations. So let us take them one by one. So if I plug it in the continuity equation, then the two terms del v, del y, del w, del z go to 0 because there is no v and w present in the flow. So I have the neat result del u del x is 0. So once I have this, I immediately conclude that and not only del u del x is 0, but all del 2u del x square and del 3u del x cube, and basically all orders of partial derivatives of u with respect to x are 0. So it means that velocity vector, which was originally written as u function of x, y, z, and t, I cap, is now further simplified into v is equal to u, which is now a function of y, z and t only. It's not a function of x, because mathematically continuity gives you del u del x is 0. So it means that u cannot be a function of x. So that's why this conclusion comes out directly from continuity. So what is the physical meaning? The physical meaning is that there is no variation of fluid velocity along flow direction, and since you are dealing with a unidirectional flow, you can say that this direction is also the direction of the streamlines. So there is no variation of fluid velocity along streamlines. Now let's start examining what can momentum equations give us. So we have the momentum equations written in terms of motion pressure. Why motion pressure? Again, because in carrying out general analysis for unidirectional flows, it is actually more beneficial to just combine the body force. Of course, this can only be done if body force is conservative. So normally, which is the case because we normally have gravity as the body force. So it is advantageous to merge it with the pressure force and therefore treat it as a single motion pressure force. So you can see that later on that what are the advantages of this approach. So the momentum equation now starts to simplify. The convective term can be written as u del x of vector v, and since vector v has a unit vector I cap which is not varying with x, so I get this result as u del x I cap, and which turns out to be 0 because del u del x is 0. So remember, इसमें u 0 नहीं है, but del u del x 0 है, जिसकी वजह से आपका convective acceleration is 0. So this is something very interesting. Unidirectional flow type 1 and type 2 configurations, the fluid particles don't have any convective acceleration. And this is the major advantage. Why? Because after all, this is the nonlinear, this is the term which imparts the complicated nonlinear character to the Navier-Stokes equation, which makes it so hard to solve. So once this convective term is 0, we expect that the Navier-Stokes equations now would be much simpler and easier to crack, you can say, or to solve. So the scalar equations are now, I am writing them. So my x direction momentum equation is written as rho naught del u del t minus del pm del x plus mu naught. Now again the second derivative with respect to x is 0, while the other two directions are retained, del 2u del y square plus del 2u del z square. So this is the x direction momentum equation, and the y and the z direction momentum equations, they don't have any velocity terms, so they just give me very elegant looking expressions for motion pressure. del Pm del y is equal to del Pm del z is equal to 0. So it shows that motion pressure does not vary along y and z directions. Now this is where it is advantageous to work with motion pressure, because if we were to retain the body forces in the original equation, then those body forces, if they have components along y and z directions, they will lead to some variations in pressure. So once the body forces are combined with the pressure forces and you are now working with motion pressure, you get these very elegant mathematical results for motion pressure. Del Pm del y is equal to del Pm del z is equal to 0, which implies that motion pressure is not a function of y and z, so it is only a function of x and t. And velocity, we have already shown, u is only a function of the u component, which is the only component, is a function of y, z and t. So I have written here in language, what does this all mean? It means that motion pressure varies along streamlines because it is a function of x, but the velocity varies normal to the streamlines because it is a function of y and z in space. So y, z are directions which are normal to the streamlines, which are straight parallel lines along x direction for type 1 configuration and type 2 configurations. So these are the simplified equations for channel and duct flows, Newtonian fluids, of course. So the advantage of this simple analysis is that whenever later on we will show you some solutions involving channels and ducts, so there my starting point would be the ending point that I have here. That means the simplified equations that I have now obtained with whatever characteristics on the velocity and motion pressure, they can be just taken from here, and solution may be carried out for any specific channel or duct flow. Okay. Now moving on to type 3, which is annular flows. Annular flows which are taking place between two concentric sort of pipes or cylinders, or there is a larger diameter pipe which is having some shaft in concentric shaft inside. So it may be a pipe or a solid rod or a shaft. So the flow takes place along the axial direction in the annular space between the two larger and one smaller concentric pipe or cylinder. Okay. So Navier-Stokes equations now you have to consider in cylindrical coordinates. So continuity equation, it looks like this. I can combine the first two terms as shown, and the momentum equations are just copied from my previous lectures where I have already derived these in cylindrical coordinates. So now this is just brought here for the purpose of correlating the analysis that we are going to carry out. Now the first category is of course for annular flows, constant flow area, because the annular area is constant along the flow direction. So the first category is, so these equations apply to both types of annular flows that were shown a few minutes ago. तो वो जो आपको दो तरह के एक टॉर्शनल तरह का एनुलर फ्लो दिखाया था जिसमें दो सिलेंडर्स थे कॉन्सेंट्रिक, इनर एंड आउटर, एंड बोथ वर रोटेटिंग काउंटर क्लॉकवाइज, तो वो भी एक एनुलर फ्लो था, उसका भी पैसेज जो है एरिया वो कांस्टेंट है. और एक हमने एक्सियल फ्लो देखा था जिसमें एक बाहर एक बड़े रेडियस का पाइप है और अंदर एक शाफ्ट या अनदर पाइप है स्मॉलर रेडियस, एंड द फ्लो टेक्स प्लेस इन द एनुलस along the length of the concentric cylinders or pipes. So that axial and torsional flows both are covered by these cylindrical Navier-Stokes equations. Now coming to axial flow first. So A axial flow. So velocity for this axial flow is Vz, and it should be Ez cap. In fact, it is incorrectly written as I cap because cylindrical coordinates में the unit vectors are er cap, e theta cap and ez cap. So please make a note of this and make a correction. Vz, which is a function of in general r, theta, z and t, all coordinates and time, and of course the corresponding unit vector ez cap and not I cap. Okay. The continuity equation, I have shown that two terms again go to 0 because Vr and V theta are 0 and we get del Vz del Z is equal to 0. So the mathematical implication is again that Vz is not a function of Z, so it is only a function of r, theta and t. So it means that there is again no variation in velocity along the streamlines, because since the flow is only axial, so streamlines will again be straight in the annulus running parallel to the axis of the concentric pipe or cylinder axis. So there is no variation in velocity along streamlines. Now coming to momentum equations. So we always examine the convective term first in the hope that if it comes out to be 0, then we are very happy because the nonlinear term of the Navier-Stokes equation is gone out of the window. So V dot del V is Vz del del Z V, and again the unit vector Ez is not going to vary with Z. So we have Vz del Vz del Z and of course E cap Z, and this term is 0 because continuity has given us del Vz del Z is 0. So yes, we are very happy that for this type 3 also, type 1 or type 2 mein to convective acceleration was 0, but in type 3 axial flow also we have no convective acceleration. So my momentum equations would become linear now, and I can write down the z direction or axial flow direction momentum equation first. So rho naught del Vz del t is equal to minus del Pm del Z, and mu naught and Laplacian of Vz. Okay, and the Laplacian operator is already written on the bottom left, so you can just apply it to Vz with the fact that del 2 Vz del Z square will be 0. So जब Laplacian इस पे अप्लाई करेंगे Vz पे, तो उसमें जो z के साथ जो सेकेंड डेरिवेटिव है उसको 0 कर देंगे, because Vz is not a function of z, already concluded from continuity equation. And the other two momentum equations which are radial r direction and theta direction, they again simplify in the same manner as with the flow configuration type 1 and 2, that del Pm del r and del Pm del theta are 0 because there are no radial and v theta velocities, so all the other terms go to 0. So again the conclusion is that the motion pressure does not vary along the radial and theta coordinates, so it can be varying only along z and of course with time. So Pm is a function of z and t, and Vz is already shown to be a function of r, theta and t, right. So these are you can say these are the simplified equations for axial laminar flows in annular geometry with constant cross section and of course Newtonian fluids. Again we observe that velocity, so again the same things that we observe for type 1 and type 2, वही चीज़ यहाँ भी ऑब्जर्व हो रही है कि velocity वैरीज नॉर्मल टू स्ट्रीम लाइन्स है ना. वेलोसिटी जो है वो अलॉन्ग स्ट्रीम लाइन वैरी नहीं कर रही है. टाइप 1 में भी नहीं था, टाइप 2 में भी नहीं था, और टाइप 3 के एक्सियल फ्लो में भी नहीं है. वेलोसिटी डज नॉट वैरी अलॉन्ग स्ट्रीम लाइन्स बट रादर वैरीज ओनली नॉर्मल टू स्ट्रीम लाइन्स, है ना. नॉर्मल से मतलब है कि आपके जो वीजेड है उसके लिए नॉर्मल डायरेक्शन होता है आर या थीटा डायरेक्शन. सो दिस इज व्हाट इट इज. while motion pressure वैरीज अलोंग द स्ट्रीमलाइन। तो यही चीज़ हमने टाइप 1 और टाइप 2 कन्फिग्रेशन में भी देखा था कि मोशन प्रेशर वॉज नॉट वेरिंग इन any direction which is normal to the streamlines, but it is varying along the streamlines। तो वही फीचर एक्सियल फ्लो में भी है। तो ये इस तरह से हमें जनरल एनालिसिस में ये एडवांटेज हो रहा है कि कुछ जनरल फीचर्स वेलोसिटी फील्ड और मोशन प्रेशर के हमको मिल रहे हैं। और अगर हम प्रेशर और बॉडी फोर्सेस को अलग अलग रखेंगे तब हमें ये कॉमन फीचर्स मोशन प्रेशर के नहीं नजर आएंगे। So that's why it's important to write equations in terms of motion pressure. Later on, pressure can always be obtained from the knowledge of the gravity or the body force. अगर एक बार आपने मोशन प्रेशर सॉल्व कर लिया तो फिर प्रेशर को रिकवर करना इज अ वेरी सिंपल एंड डायरेक्ट एक्सरसाइज। सो नाउ कमिंग टू टाइप 3 का जो दूसरा टाइप ऑफ फ्लो है, एनुलर फ्लो है, टॉर्शनल एनुलर फ्लो। देर आर टू, रिमेंबर, टाइप 3 में एक एक्सियल एनुलर फ्लो है और एक दूसरा टॉर्शनल एनुलर फ्लो। सो टॉर्शनल एनुलर फ्लो जैसा कि मैंने दिखाया था कि सिनेरियो बन सकता है दो कॉन्सेंट्रिक सिलेंडर्स जिनमें या तो दोनों को ही रोटेट किया गया हो डिफरेंट एंगुलर वेलोसिटीज से, काउंटर क्लॉकवाइज या क्लॉकवाइज, ओमेगा 1 ओमेगा 2, या फिर दोनों कॉन्सेंट्रिक सिलेंडर में से कोई एक रोटेट किया गया हो एटलीस्ट। ओके, एंड you can even talk of a single cylinder placed immersed in a fluid which is rotating, or fluid inside a single cylinder or a container, cylindrical container, which is being rotating। तो सिंगल सिलेंडर भी हो सकता है कन्फिग्रेशन, और डबल कॉन्सेंट्रिक सिलेंडर कन्फिग्रेशन भी हो सकते हैं फॉर टॉर्शनल एनुलर फ्लोज। सो अगेन द कॉन्टिन्यूटी इज सिंप्लीफाइड, उसमें जो रेडियल और जेड डायरेक्शन टर्म है दैट इज 0, and we are left with 1/r del v theta is 0. So again we conclude that v theta cannot vary along theta direction. So v theta is a function of r, z and t, and of course it implies that velocity does not vary along streamlines. So ये feature जो है velocity does not vary along streamlines, ये बड़ा consistent सा feature है जो अभी तक सारे flow configurations में हमारे सामने आया है और surface किया है। Now let us look at the momentum equation. Again सबसे पहले वही v dot del v term, and we examine it very carefully now because I am having v dot del v as v theta r del del theta। चूँकि बाकी वेलोसिटी 0 हैं तो इसीलिए v dot del जो है उसमें खाली एक ही टर्म होगा, v theta by r del del theta। And this time since vector v has e theta unit vector, so I have to be careful because it has to be differentiated with respect to theta. So I get two terms inside, and finally I get a value which is not 0, minus v theta square by r e r cap. So it means that there is a radial acceleration in such torsional annular unidirectional flows। ये जितने भी torsional annular unidirectional flows हैं इन सब में एक radial acceleration होगा convective, minus v theta square by r e r cap। इनफैक्ट ये जो एक्सेलरेशन है ये वही एक्सेलरेशन है जो एक जब हम एक कर्व्ड पाथ में किसी पार्टिकल को मूव करते हैं तो जो कर्व पाथ का इंस्टेंटेनियस सेंटर है उस तरफ एक सेंट्रीपिटल एक्सेलरेशन होता है। सो दिस माइनस वी थीटा स्क्वायर बाय आर इज एग्जैक्टली दिस सेंट्रीपिटल एक्सेलरेशन ऑफ ऑल फ्लूइड पार्टिकल्स, एंड देयरफॉर इट इज इन द नेगेटिव रेडियल डायरेक्शन डायरेक्टेड इनवर्ड्स टुवर्ड्स द सेंटर। So the radial direction equation now will contain this acceleration term, so minus rho naught v theta square r and is equal to minus dm del pm del r plus mu naught, and since there is no radial velocity so all the radial velocity terms are 0, and even the v theta term goes to 0 because continuity has shown that v theta is not a function of theta. So all the viscous flow terms in fact vanish. So this is interesting. For a torsional annular flow, when we write the momentum equation in the radial direction, the momentum equation does not contain any viscous force. So although fluid viscous है ना, viscosity भी है, viscous flow है, but the equation and the behavior of the torsional annular flow is such that of course हम एक इनकम्प्रेसिबल होमोजेनस कांस्टेंट प्रॉपर्टी फ्लो ले रहे हैं न्यूटोनियन फ्लूइड का, तो वो सब बातें अपनी जगह साथ में भी हैं। तो उसमें क्या होता है कि हमारा जो रेडियल डायरेक्शन इक्वेशन है वो बिल्कुल एक इनविसिड फ्लो का इक्वेशन आ जाता है। एंड थीटा डायरेक्शन इक्वेशन यू कैन सी देयर आर नंबर ऑफ टर्म्स। विस्कस फोर्स में देयर आर सम टर्म्स विच गो टू ज़ीरो, जितने भी डेल बाय डेल थीटा टाइप के टर्म्स हैं, डेल 2 वी थीटा, डेल थीटा स्क्वायर, दैट विल बी ज़ीरो बिकॉज वी थीटा इज़ नॉट अ फंक्शन ऑफ थीटा। जो वी आर वाला टर्म है वो भी ज़ीरो होगा। बाकी टर्म्स जो वी थीटा के रेडियल डेरिवेटिव्स हैं दे विल रिमेन बिकॉज वी थीटा इज़ अ फंक्शन ऑफ आर, सो एंड ऑफ कोर्स ऑल्सो ऑफ जेड, सो आई हैव retained that here right now for the time being ये थीटा डायरेक्शन का ये इक्वेशन आ गया सिंप्लीफाई होके, एंड जेड डायरेक्शन इक्वेशन इज very much similar to what we were getting for some of the other unidirectional flows so far. So 0 minus del pm del z is 0. So it means that motion pressure does not vary along z direction, and motion pressure is a function of r, theta and t only. Right. So further now if we take a close look at the theta direction momentum equation, we can simplify the scenarios further also, है ना। अभी थोड़ा सा इसका जो torsional annular flow है, the analysis is not really over. We can do a deeper analysis and deduce more information about the flow, rather not reduce but deduce more information about the torsional annular flow. So if I consider the theta direction equation and if I rearrange the terms, so one thing we can observe from this rearranged equation, that what is on the left we have motion pressure derivative with respect to theta, right? So now since pm is in general up till now we say that it is a function of r, theta and t, so it means that the left hand side can be a function of r, theta and t. But what is on the right hand side? We have only velocity v theta derivatives, right? And since v theta is a function of r, z and t, so we can expect all this terms finally giving me on the right side a function of r, z and t. So the above momentum equation says that LHS is equal to RHS, and so it looks a bit strange that the RHS, which is a function of R, Z and T, is actually equal to a function which is a function of R, theta and T. तो ये possible mathematically नहीं है, because one side you have a function of R, Z and T and the other side you have a function of R, theta, T. तो सोल्यूशन इज ओनली पॉसिबल, या ये पॉसिबल जब ही है, इस इक्वेशन से मीनिंगफुल सोल्यूशन जब ही निकाले जा सकते हैं जब लेफ्ट हैंड साइड और राइट हैंड साइड दोनों फंक्शन ऑफ आर एंड टी ओनली हों। ओके, सो दैट इज व्हाई आई हैव रिटन दिस, क्योंकि अगर थीटा और जेड रिटेन करेंगे आप तो फिर दोनों साइड विल नेवर मैच फॉर ऑल वैल्यूज ऑफ आर जेड टी एंड आर थीटा टी। ओके, so differential equation should match for all coordinates and time. So जो आपके missing coordinates on other side, for example आपका जो left side है उस पे सिर्फ theta coordinate r theta t का function है, और जो आपका right hand side है वो r z और t का function है। तो ये इस तरह के differential equation से solution is only possible अगर हमारी दोनों sides r और t का function हो अलोन। ओके, ना तो z डिपेंडेंस इधर होनी चाहिए ऑन द राइट साइड एंड ना ही थीटा डिपेंडेंस होनी चाहिए ऑन द लेफ्ट साइड। सो दिस शोज दैट डेल पी एम डेल थीटा जो है वाला जो टर्म है वो खाली r और t का फंक्शन होगा, होना चाहिए रादर, एंड वी थीटा शुड ओनली बी अ फंक्शन ऑफ आर एंड टी। ये सॉल्वेबिलिटी की कंडीशन है। अगर आप थीटा डायरेक्शन के मोमेंटम इक्वेशन को देखें तो उससे जो सॉल्वेबिलिटी कंडीशन है वो ये आ रही है निकल के अबाउट वी थीटा एंड डेल पी एम डेल थीटा। तो इससे ये पता लगा कि वी थीटा जो है, जो अभी तक हम आर और जेड और टी का फंक्शन मान रहे थे टॉर्शनल एनुलर यूनिडायरेक्शनल फ्लो के लिए, वो एक्चुअली आर और टी का ही फंक्शन हो सकता है, जेड का फंक्शन नहीं हो सकता। तो इसका मतलब जो सेकंड डेरिवेटिव है वी थीटा का जेड के रिस्पेक्ट में, दैट हैज टू बी ड्रॉप्ड। एंड नाउ लेट अस मूव फर्दर। डेल पी एम डेल थीटा जो है वो हमारा फंक्शन आ गया है आर और टी का, बट देर इज अ प्रॉब्लम इन दी अबव डिडक्शन। ये जो ऊपर का जो डिडक्शन आया है डेल पी एम डेल थीटा के बारे में, फंक्शन ऑफ आर एंड टी, इसमें एक प्रॉब्लम है। लेट अस लुक एट दिस प्रॉब्लम व्हाट इट इज। थोड़ा सा डीपर जाना पड़ रहा है, बट द रिजल्ट्स आर वेरी नाइस एंड एलिगेंट, सो दैट्स व्हाई इट इज वर्थ डूइंग इट। सो सिंस एट अ फिक्स्ड आर एंड एट अ गिवन टाइम टी, ये जो फंक्शन होगा इसकी कोई वैल्यू होगी, राइट। सो ये जो डेल पी एम डेल थीटा मैंने लिखा हुआ है फंक्शन ऑफ आर एंड टी, अगर मैं आर फिक्स कर लूँ थोड़ी देर के लिए, किसी एक आर पे बात करते हैं और एक सर्टेन टाइम इंस्टेंट पे, तो ये फंक्शन एक वैल्यू देगा। नाउ दैट वैल्यू इफ इट इज नॉट इक्वल टू जीरो, तो दो ही पॉसिबिलिटीज हैं, या तो वो पॉजिटिव होगी या नेगेटिव होगी। कांस्टेंट भी होगी उस आर और टी के लिए, मतलब एक पर्टिकुलर टाइम इंस्टेंट पे पूरे आर वैल्यूज के लिए वो एक कांस्टेंट वैल्यू होगी, और वो कांस्टेंट अगर जीरो नहीं है तो फिर वो पॉजिटिव हो सकता है या नेगेटिव हो सकता है। सो दैट्स आई हैव रिटन देन डेल पी एम डेल थीटा is either positive or negative, and it, remember, it will be a positive or a negative constant. Okay, so this implies that pm either increases or decreases depending on whether the derivative is positive constant or negative constant. So pm either increases or decreases linearly with theta as theta varies from 0 to 2 pi at that radius. तो जिस रेडियस पे भी आप इस वक्त लेट्स से वी आर टॉकिंग एंड एनालाइजिंग, तो उस रेडियस पे थीटा को 0 to 2 पाई वेरी करेंगे अगर, तो पीएम लीनियरली या तो इंक्रीज होगा या डिक्रीज होगा अगर फंक्शन की वैल्यू 0 नहीं है तो। सो लेट अस सी व्हाट दैट इज गोइंग टू लीड टू। दिस इज नॉट अलाउड, ये लीनियर वेरिएशन ही अलाउ हो सकता। वाई? बिकॉज पीएम वुड देन हैव अ डिसकंटिन्यूटी एट थीटा इज इक्वल टू 2 पाई। जंप डिसकंटिन्यूटी आ जाएगी थीटा इज इक्वल टू 2 पाई। लेट अस अंडरस्टैंड दिस ग्राफिकली। So I am plotting Pm with respect to theta with a fixed value of r and a fixed value of t. तो r और t को मैंने फिक्स कर दिया है certain values पे, और सपोज डेल Pm डेल थीटा मेरा पॉजिटिव है। तो पॉजिटिव का मतलब है कि कांस्टेंट स्लोप है, तो इसका मतलब एक स्ट्रेट लाइन, इसमें थोड़ा सा यू पार्डन मी फॉर ड्रॉइंग सम कर्व्ड लाइंस, तो कर्व्ड लाइंस को इग्नोर कर दीजिए। आई हैव लेटर ऑन ड्रॉन इन बोल्ड स्ट्रेट लाइंस। ओके, तो स्ट्रेट लाइन इसलिए बिकॉज डेल पी एम डेल थीटा की वैल्यू कांस्टेंट होगी। तो अगर पॉजिटिव है तो पॉजिटिव स्लोप के साथ आई एम ड्रॉइंग द लाइंस। सो 0 से 2 पाई तक जाते जाते वो लीनियर एक स्ट्रेट लाइन ट्रेंड फॉलो करेगा, और जैसे ही 2 पाई को, यानी 2 पाई का मतलब है फुल सर्कल, नाउ थीटा कैन बी टेकन फर्दर। ओके, फिर से आप रोटेट करके अगेन एक सेकेंड राउंड भी जा सकते हैं। तो 2 पाई से फिर 4 पाई फिर चले गए। तो अगर 2 पाई से 4 पाई फिर जाएंगे तो जैसे ही आप 2 पाई के बाद अगेन फिर से सेकेंड राउंड लेने लगेंगे, तो वेलोसिटी, द मोशन प्रेशर वुड देन जंप डिसकंटिन्यूअसली बैक टू दी जीरो वैल्यू, बिकॉज वो लीनियरी वेरिएशन है 0 to 2 पाई with a positive slope. So जो second round होगा वो again effectively you are going through the same points again. तो same points का मतलब है same values will be seen again. तो 2 पाई से 4 पाई जाने में आपको मोशन प्रेशर की वही वैल्यूज मिलनी चाहिए जो 0 to 2 पाई जाने में थी, बिकॉज यू आर गोइंग थ्रू द सेम पॉइंट्स इन द फ्लो डोमेन। तो अगर ऐसा होगा तो एक जंप डिसकंटिन्यूटी आ जाएगी 2 पाई पे, as I have shown, and I have encircled it with red. Now the same scenario is going to result if you have del pm del theta is negative for some fixed value of r and t. So this time the opposite is there. I have a negative slope straight line behavior. So 0 to 2 pi the motion pressure would decrease to a minimum value at 2 pi, and then again the same values repeat for 2 pi to 4 pi. So since there is a repetition, so you are bound to get a jump discontinuity at 2 pi, again encircled in red. So these such type of discontinuities are not physical. ये ऐसा नेचर में या फ्लूइड्स में ऐसा नहीं हो सकता कि आपको एक पॉइंट के दोनों तरफ एब्रप्ट जंप्स मिले वैल्यूज में, प्रेशर की, मोशन प्रेशर की, या किसी भी वेरिएबल की. सो आर नॉन फिजिकल एंड कैनॉट एग्जिस्ट. देयरफॉर आवर डिडक्शन दैट del pm del theta is a function of r and t leads to non physical solutions. तो ये जो डिडक्शन था जो कि थीटा डायरेक्शन मोमेंटम इक्वेशन के बैलेंस की वजह से आया था कि v theta should only be function, can only be allowed to be a function of r and t, and similarly del pm del theta can be a function of r and t, leads to general deduction जो है leads to non physical solutions. और ये इसलिए आ रहा है बिकॉज एक किसी भी पर्टिकुलर r और t के लिए इस फंक्शन की वैल्यू अगर जीरो नहीं होती है तो ये प्रॉब्लम आएगी. सो विच मीन्स सपोज अगर जीरो होती है इसकी वैल्यू, तब क्या प्रॉब्लम आएगी? देन वी कैन वेरी इजीली सी दैट द प्रॉब्लम इज एसोसिएटेड विद नॉन जीरो वैल्यू ऑफ del pm del theta और दिस फंक्शन विच इज अ फंक्शन ऑफ r and t. अगर सपोज ये फंक्शन ही जीरो वैल्यू देने लगे फॉर ऑल r and t, ओके, सो इफ इट गिव्स मी अ जीरो वैल्यू for all r and t, then del pm del theta will be 0. तो इसका मतलब ये हुआ कि pm would be constant, है ना, 0 से 2 pi तक. तो अगर वो constant है 0 से 2 pi, then even when you go for the second round from 2 pi to 4 pi, the same constant value will continue and the jump discontinuity would be eliminated. So this is the beauty of all this analysis, that I finally concluded that the only physically realistic scenario is that del pm del theta must be 0 for all r and t. Hence for torsional annular flow we conclude final conclusion हमारा क्या है? V theta must be allowed to vary with r and t only. So V theta is a function of r and t, and the motion pressure is also allowed to be a function of r and t only. Now so the velocity and motion pressure do not vary along streamlines. इस केस में थोड़ा रिजल्ट फर्क है, खाली वेलोसिटी नहीं, मोशन प्रेशर भी वैरी नहीं कर रहा है along streamlines. This is different from the previous types of flow configurations जो हमने देखे, मतलब type 1, type 2 as well as the axial annular flow of type 3. उसमें हमें velocity does not vary along streamlines and motion pressure varies along streamlines मिला था. यहाँ पे हमें दोनों ही streamline के along vary नहीं कर रहे हैं. So this is also compatible with r direction momentum equation. अब आप इस information को जो v theta is function of r and t and pm as function of r and t, इसको check कर सकते हैं कि ये compatible है with my radial direction momentum equation. What is the radial momentum equation? Rho naught v theta square by r del pm is equal to del pm del r. तो यहाँ आप देख सकते हैं कि अगर दोनों साइड पे v theta और pm जो है खाली r and t का फंक्शन है, तो there will be no problem of getting solutions left hand side और right hand side से, compatibility की प्रॉब्लम नहीं होगी इक्वेशन में. So this is perfectly acceptable. So my final equations, the Govan equations are simplified. The Govan equations are for torsional unidirectional annular flow, rho naught. So pardon me for missing that rho naught. Okay, left side पे rho naught v theta square r, density है rho naught, is equal to del pm del r, and the theta direction equation interestingly does not contain any motion pressure term. तो ये भी पहली बार ऐसा हुआ है. इससे पहले किसी फ्लो कोई भी जो कैटेगरीज या फ्लो कॉन्फ़िगरेशंस यूनिडायरेक्शनल फ्लोज के हमने देखे हैं अभी तक, उनमें किसी में भी वेलोसिटी का इक्वेशन प्रेशर से डिकपल नहीं हुआ था. लेकिन टॉर्शनल यूनिडायरेक्शनल एनुलर फ्लो ये पहला हमारा एग्जांपल ऐसा आया है टॉर्शनल यूनिडायरेक्शनल एनुलर फ्लो का, या फ्लो का सिंपली, जिसमें के वी थीटा का जो इक्वेशन है उसमें से प्रेशर हैज बीन रिमूव्ड totally, and so the pressure has no role in influencing V theta. Rather, it is the other way around. Once V theta is solved from the second equation, we put it back in the first radial direction equation to get the motion pressure solution. So velocity V theta is influenced, not influenced by motion pressure, but it influences the motion pressure. Okay. Now, last thing that I can conclude about this of annular flow, torsional annular unidirectional flow, is that I examine the radial equation and say that rho naught V theta square by R is positive because it contains the square term V theta square. So, since it is positive, it gives me del Pm del R as positive. So, in space, you can say that the radial derivative of motion pressure is positive. So, it shows that motion pressure is a monotonically increasing function और Pm increases monotonically along radial direction. तो जैसे जैसे आप रेडियस बढ़ाएंगे या आप ये कह सकते हैं कि जो सर्कुलर स्ट्रीमलाइंस हैं आप उनकी कॉन्केव साइड से कॉन्वेक्स साइड की तरफ जाएंगे तो मोशन प्रेशर विल कीप ऑन इंक्रीजिंग. ओके. So, since this lecture is a bit elongated one, so I have deliberately split it into two parts. So, the remaining type 4 radial flow, unidirectional radial flow, configuration type 4, that will be discussed in the second part of lecture 16. Okay, thank you very much.